To finish up looking at special parallelograms here, we have two problems. One of them involves some overlapping special parallelograms and the angles that are involved. The other one is a proof using some congruent triangles and a parallelogram in order to prove that we have a special parallelogram, being that we're looking for a rhombus. So let's start by looking at the first set here. They gave us some information in the instructions. You definitely want to read your instructions. It says that BDEG is a rectangle. So BDEG being a rectangle means that we have right angles in each corner, means that our diagonals are congruent to each other, means that those diagonals are creating those isosceles triangles, and going to help us to find all of our angles in that rectangle. We also have a rhombus. It says that ABCD is a rhombus. So ABCD, and that has part of that figure is overlapping in that rectangle. So let me zoom in and let's start looking at what we have here. So in the rectangle, I have one angle given to me that's 63 degrees. And being a rectangle, I know that that corner angle adds to 90. So I'm able to find the angle next to it by subtracting from 90. I'm getting 27. Using my isosceles triangle relationship within this rectangle, I'm able to put the 63 here, as well as here, as well as here. Using those isosceles triangles in the rectangle, I can put the 27 here and here and here. Now that I have those angles for the rectangle labeled, I can also find some of the angles that are located at C. If I kind of focus in on this triangle, knowing that the triangle sum is 180, I've got 63 and 63. Subtracting from 180 is 54. Using vertical angles, I'm able to label this one as 54 as well. Now we kind of have to start looking at the rhombus. There is a rule about rhombuses that we need to remember, and that is that the angles of a rhombus along a diagonal are equal to each other. So right here, right here, right here, and right here are all congruent angles. And some of those are already labeled with 27s, so we're able to bring those 27s to the other side of that diagonal as well. Another thing that's true for a rhombus is that the diagonals are perpendicular. So we can add a right angle marking here, showing that all four of those angles in the center there are 90 degrees. Now we can, let me get a highlighter here, focus on one of the triangles within the rhombus. It's a right triangle, and one of the acute angles is 27. And we can subtract from 180 that triangle sum and solve for our missing angle, getting 63. And using the property that states that the diagonal of a rhombus will bisect its opposite angle pairs, allows us to get 63 there, and here, and here. Using vertical angle pairs, we can get 63 here and here. So lots of angles that we're able to know there. And we can use triangle sum again down here in order to even figure out that this would be a right angle here as well. So basically everything is marked now, and now it's just a matter of finding the angle using the 3 letters in the name and identifying what that angle would be. Locating angle GDB. GDB. So GDB, right there, is that 27-degree angle. ABC. A to B to C. You would have to put together the two 27s. That will be 54. DAB, D to A to B, putting together both of the 63s. That will be 126. BCG, B to C to G outlines that 54-degree angle. GCE. G to C to E puts together those two 63s, 126. DEG, D to E to G, that is a 90 degree. It's one of the corners of the rectangle. AHB, A to H to B, that is one of the right angles at where the rhombus's diagonals are intersecting, 90. DGB, D to G to B outlines that 63 degree angle there. So lots of answers for this one question. Means if you're ever asked anything like this, it's going to be quite a lot of points involved. So make sure you are able to find all of your related angles based off of your types of figures. All right, our last one in today's notes is a proof, and we are given some congruent triangles. We are given triangle GEC, and this actually has a typo, not in the triangles, but in part of it. GEC is congruent to GHX. So those triangles are congruent to each other. We are also given a parallelogram, but notice it has two of the same letter in it. BEBH. Should say BEGH. So replace that B with the letter G. Just had a typo there, saying that that is a parallelogram. So they're saying this right here is a parallelogram. Our goal is to prove that GEBH is a, and I'm going to go ahead and I'm going to be weird and I'm going to make this GEBH. That way it matches that GEBH. They want us to take the parallelogram and prove that it's a rhombus. So you want to kind of think about properties of parallelograms that are going to help us, use that to get to the fact that it's a rhombus. In order to prove that we have a rhombus, we have to prove that all of the sides are congruent to each other. And so with a parallelogram, we do know that the opposite sides are congruent to each other. So I could say that these are congruent and that these are congruent. But to be a rhombus, they have to all four match. So if we have a way to prove that a consecutive set of sides is congruent to each other in this parallelogram, then we can say it's a rhombus. Using our congruent triangles, we notice that GE and GH are a pair of corresponding sides. And they are consecutive sides of the parallelogram. So if we're able to use our congruent triangles to show that those pieces are congruent, then we can use transitive property to show all of the sides to be congruent to each other. So that's going to be my plan. So we're going to start with our given, GEC congruent to GHX. And we're also given GEBH is a parallelogram. So I'm going to start with identifying my opposite sides of my parallelogram to be congruent to each other. So I'm going to say that GE is congruent to HB. And I'm going to say that GH is congruent to EB. And the reason there would be if parallelogram, then opposite sides congruent. I'm going to now use the congruent triangles in order to say that GE is congruent to GH by CPCTC. Corresponding parts of congruent triangles are congruent. Since I now know that GE matches with GH, and we had GE matching with HB and GH matching with EB, we're now able to use transitive property to link all of these together. So I'm going to write like one huge congruent statement. So GE congruent to HB, congruent to GH, congruent to EB. Just everything, all four of them are congruent now through the transitive property of congruence. And since all of the sides are congruent, we can now say that we have a rhombus. And my reason is going to be if quadrilateral with four congruent sides, then parallelogram. Not parallelogram. I was going for rhombus, then rhombus. There we go. All right, so that is a proof involving parallelograms and special parallelograms.